Hi everybody, Physics Ninja here, and welcome to my big review on induced EMF, Faraday's law, Lenz's law, magnetic flux, resistance, loops falling, loops rotating, magnetic fields changing. All right, any kind of problem you can think of, we've got it in this problem set. What I've done is I put together 9 problems. There's 28 questions dealing with all kinds of scenarios. All right, so what I recommend you doing, just like before, okay, so we're going to start by going to get the problem set. PDF document, the link is in the description. Look at it, start solving some of the problems, then come back to the video and see if we get the same answer. Physics is not a spectator sport. You can't just watch these videos and think this is exactly how I would solve it. That's not how it works. You need to sweat it out a little bit. So, like with all my videos, if you like it, give it a thumbs up. Consider subscribing to Physics Ninja. It is the best way to support what I do. All right, let's get started. All right, here's our first problem. We have a circular conducting metal loop of radius 3 centimeters. It lies in this XY plane. It's placed in a spatially uniform but time-varying magnetic field, which is oriented parallel to the z-axis. Note the positive z-axis is pointing out of the page. The loop has a resistance of 5 ohms. The magnetic field has a sinusoidal time dependence that's given by this expression, and they give you these constants and also that frequency. All right, the first question says, which way is the current circulating in the loop at time equals to 0.5 seconds? So let's identify where that time of 0.5 seconds, it's right here. Now what you could do is you could look just a little bit before or just a little bit after. It really doesn't matter. I'm going to start by looking a little bit before. So what is going on before is the field is positive and the field is getting smaller, and it's 0 at 0.5 seconds. So how would we find the direction of the current? This is an application of Lenz's law, right? We see that in this kind of region over here, we have that our flux is reducing. So what do we want to do? Lenz's law tells us that the coil or the metal loop here wants to oppose the change in flux. Let me just write that down. So oppose the change in flux. So the way that it does that is it's going to produce an induced magnetic field, okay? It's going to generate flux to oppose that change. So if the field, for example, is getting smaller here, I mean that the B induced then has to also be outside of the page in this kind of region over here. So if I have an induced magnetic field that is coming out of the page like that, here you have to use your right-hand rule, and you should find that the current here must be flowing in that direction. That is the direction of our induced current, and that corresponds to the counterclockwise direction. All right, that's a great problem and a great test. Now you can also do it over on this side a little bit, right? You go where the field starts at 0 and then it starts increasing in magnitude, but the field's in the opposite direction. You're going to get the same answer. All right, next question says, what is the magnetic flux through the loop at time equals to 2 seconds? Time equals to 2 seconds is right here on our graph. We see that we have a magnetic field right here of 3. You've got to be careful with the units, so that is actually 3 Tesla. So they're asking us for the magnetic flux, so we apply our definition. The field is uniform in space, so I don't need any fancy integral over here. So it's simply B scalar product with the area. Again, the area is going to be pointing in the z direction, that vector, and also our magnetic field is in the z direction. Therefore, we also don't have to worry about the angle between the loop and the magnetic field, so this just reduces to B times the area, and we're looking at the area of a loop, which is pi r squared. Next thing we do now is simply substitute in our values. Okay, so we get 3, I get pi, and the radius of this loop was 3 centimeters, 0.03. Don't forget to square that. Put those numbers in the calculator. You should get 8.48 multiplied by 10 to the minus 3. That should be in Tesla meters squared. All right, the correct answer for this one is choice B. All right, we've got 2 more questions related to this problem here. Let's go to the next page. All right, next question says, which way is the current circulating in the loop at time equals to 1 second? So let's go see what the field is doing at time equals to 1 second. We are right here down at the bottom. If I want to calculate that current, that's, well, here they're just asking me for the current direction. Well, let's think about this for a minute. What is the induced EMF at that specific time. I'm just worried about the magnitude of the induced EMF at that time. What I need to evaluate is how does the flux change with respect to time. Again, the flux is defined as the field multiplied with the area. Now the area is not changing, so we could take that outside of the derivative, and we're left with an expression that just looks like this: area multiplied by the rate of change of that magnetic field at that time. That is really nothing more than the slope of B versus T at that instant in time. And you can see right here that the slope here is actually 0. Therefore, we conclude that there is no current at that time since there's no induced EMF in that loop. All right, last problem here, or last question for this problem says, calculate the magnitude of the current now at time equals to 0.8 seconds. So let me go ahead and clean this up. So we're looking now at a specific time. Luckily, they gave us an expression here for the field at every single time, so we don't really have to rely on the graph information. What I'm going to do is I'm going to use my expression up above, but I need to evaluate this derivative of the field with respect to time. So again, this is going to give me my induced EMF. If I am looking for the current, well, my current here is going to be that magnitude of the induced EMF divided by the resistance of that loop, which they told me was 5 ohms. All right, so here we have to evaluate this. This is going to be the area of the loop, that's pi r squared, divided by the radius, and now I have this rate of change of the magnetic field. You have to differentiate this function. If I differentiate the cosine, I'm going to get a sine, and you use the chain rule, there's going to be a 2 pi f that will come out in the front. So this should look like this: B0, the amplitude, multiplied by 2 pi f, and multiplied by sine of the exact same argument here, 2 pi f multiplied by time. Okay, now we have to be very careful. There are a lot of numbers to substitute into here, so just be very careful when you do this. Pi we know, the radius is 0.03. Square that. B0 is that field amplitude, that is 3. Now we have another 2 pi, the frequency is 0.5 hertz. And now we have all of this. Make sure your calculator is in radians here, or convert everything to degrees and just be careful. Now the time that we are substituting in here corresponds to this of 0.8 seconds. All right, the last thing I need to divide through by that, by the resistance of that loop, which is 5 ohms. All right, at the end, I put the numbers in the calculator, and I should get 3.13 multiplied by 10 to the minus 3. That's measured in amps. So 3.13 milliamps, that corresponds to choice C. All right, that's it for this problem. Let's go look at problem 2. All right, here's problem 2. A square conducting metallic loop is moving in the x direction through a region of space with a magnetic field pointing along the negative z direction. The loop has dimensions A equals to 20 centimeters and a resistance of 2 ohms. The magnitude of the magnetic field increases linearly in the x direction, where A is a constant given by 100 Tesla per meter. All right, the first question here says, calculate the flux through the loop when the left edge, this edge right here, is at a position of x equals to 0.7 meters. All right, only consider the field due to the, the flux due to the external field. All right, that's the field produced by this. So how do we calculate the flux? We use our definition, the magnetic flux. Now in this case, the field is not constant in space. So what you have to do here is we really need to integrate over the entire loop area, and we integrate the value of the field over that area. So this here is a two-dimensional integral, and the value of b is given by that constant multiplied by x, and my little patch of area here inside that square loop is dx dy. So let's think about what our limits of this integral are. So here I'm going to be integrating in the y direction, say from 0 all the way to the height of that loop. So for the y, it's 0 all the way to a. And in the x direction here, we have to be a little bit careful because we're looking for the flux at this specific instant in time. So we're integrating from that initial value, which is, say, the left-hand side of 0.7. And that means that the other side has to be 0.9. Also over here, I could just substitute by 0.2 because the loop edge has a 20 centimeter length. All right, so what can I do now? Now this is a pretty straightforward integral. What you do is you take the constant a outside of that integral, That's just 100 Tesla per meter. This integral now becomes x squared over 2 multiplied by that distance a. And here I have to substitute the limits from 0.7 all the way to 0.9. All right, now let's just go ahead and substitute. So we get big A, little a, and just rearrange this a little bit between those limits. All right, now substitute the numbers. I get 100 for that. The length of side A is 0.2 meters. I still get the 1/2 factor from the integral. And here I'm left with 0.9 squared minus 0.7 squared. All right, put those numbers in the calculator. At the end of the day, I should get 3.2 Tesla multiplied by meters squared. All right, and that there corresponds to choice C. All right, for problem 2, let me just start off with a clean page over here. It says, calculate the force on the loop when the left edge of the loop is located at x equals to 2.3 meters and moving at this velocity. All right, so we have different forces. Look at all the forces are negative, so it tells me that the net force here should be pointing to the left. Let's go see why that happens. As the loop is moving here to the right at this velocity, look what happens. There is more field lines going through the loop, so that means that the flux is increasing. Lenz's law says that there's going to be an induced magnetic field that is going to be coming out of the page. This is the direction of B induced. If there's a B induced, it means there is a current that is induced in that loop that is going to go in this counterclockwise direction. All right, once you know this, now you can go ahead and calculate our magnetic force on each of those segments. Remember, the magnetic force is given by I, L cross B. So you have to use the right-hand rule in order to calculate the direction of the force, and the magnitude we can easily calculate. But let's go ahead and do this. Look what we have here. We have a magnetic force in that direction. Here along every segment, the field is different, but when you sum all those up, you're going to get a magnetic force which is acting down. At the bottom segment, you have a magnetic force that's acting up. Both of these are going to cancel out because they're always equal and opposite direction. How about on the left-hand side? Left-hand side, you also have a magnetic force. In this case, it's acting to the right. Now, the one that we are most interested in is the left and the right combination here. Because the field is stronger on this edge, this force is going to be bigger, so that's why that net magnetic force has to be pointing to the left-hand side. So this is how I would write it. The net magnetic force is going to be the magnetic force on the right-hand side minus, let's put minus for that one, and plus the magnetic force here on the left-hand side. All right, so how do we calculate this? Well, how do you calculate the magnetic force? Again, the current and the field are perpendicular to each other. So for each one of these, all I need to know is what the current is, what the length of that side is, and multiplied by the field at that position. So how would this look like? So for the right-hand side, we have minus. The current is going to be that induced current, which I'm going to need to calculate. The length of the side is actually A. And then the magnetic field here, I'm going to have to do the magnetic field here on the right-hand side. Plus, what is the magnetic force on the left-hand side? Again, it's the current, the length of the side, and multiplied, what is the magnetic field here on the left-hand side? Okay. So we have a lot of things to calculate. The magnetic field you can easily calculate, right? It's simply A times X. And we're evaluating this when X is at 2.3 meters. So I'm going to go ahead and just factor this out. This is the same for both. And here I'm left with BR, the right-hand side, plus BL, or minus BL. Oh my gosh, I'm making a couple sign errors over here. All right, so I'll come back to that induced current in just a minute, but let's worry about this side. The field here on the right-hand side is going to be that constant A, and that right-hand side is a distance of X plus A. Okay? Remember, they're telling us what the position of the left-hand side of the loop is, the left edge of the loop. So right here, we would have that same constant A multiplied by that X value, which is going to be our 2.3 meters. Notice that this term here is going to cancel with this one, so we really don't need to worry too much about that one. All right, at the end, we're going to be left with minus I multiplied by, again, combine all of this, you're going to get a squared and multiply by that constant A, which is 100 Tesla per meter. All right, this is how you calculate this magnetic net force. We know all these concepts, but I still haven't calculated what the induced current is. So now I need to work on that. What is the induced current for this loop? Again, for that, we have to look at what is the induced EMF divided by that total resistance of that loop. And this induced EMF is the change of flux with respect to time. And again, I still have my 1 over R for the resistance term. So how would we calculate this change of magnetic flux? Well, we have to do something similar to what we did before. You can first calculate the flux and then differentiate it with respect to time. All right, so I'm going to continue with this. So let's first calculate what the flux is at this instant in time. Again, I have to integrate that field expression, which makes this a little bit harder, okay? So let's evaluate this double integral. This goes from 0 all the way to a in the y direction, and here it goes from x and all the way to x plus a. And I'm looking at the field with that area. So this is dx and dy. Our field is given by that expression, that constant a multiplied by x. All right, so be careful when you evaluate this term over here. We're going to have an a for the integral over dy. And now we have to evaluate this. We have another constant a that comes out. And here I'm left with x squared over 2 again, evaluated between two different limits than the previous problem. Okay, so this is what you have. You have ax over 2. I'll open up a big bracket. Here we're going to have x plus a squared and then minus x squared. Okay, so this is the flux at that specific instant in time, but we're interested in the induced current. So the induced current, we need to evaluate this. How do you evaluate the change of flux with respect to time? In order to do that, let's go ahead. So I am running out of space here. We're going to have to go to a new page soon, but we could still finish this. D phi over dt. Okay, how do we do this? Well, now for this I would use the chain rule. I have a function of flux that is a function of x only. So what I could do is I can differentiate the flux with respect to x. That's pretty easy to do. And then all I do now is multiply by dx over dt. And guess what? This here is really nothing more than the speed or the velocity at that instant in time. So you need to evaluate this and multiply by that velocity. So how would you differentiate this? So d phi over dt looks like this. I still leave all the constant terms the way they are. Those don't change. Now I'm going to be left with 2x plus a minus 2x. And you could see that those 2x factors actually will cancel out with each other. So that is really nice for us. And I can't forget to multiply by that velocity term, which I have just kind of forgotten about. All right, so the last expression now for d phi over dt, this reduces kind of nice. That actual 2 cancels with this one, and I'm left with little a squared, big A multiplied by the velocity. That is the change of flux with respect to time, which we needed to calculate what this induced current is. So you go back to the current expression over here that we have. This is a squared, big A, the velocity divided by the resistance. Okay, wow, this is a really, really long problem. What I'm going to do now is we're going to have to create some more space. Yeah, let's copy all of this, put this to the top. This is where we had started. We've taken a little detour to calculate what that induced current is, but now I can go ahead and substitute this expression. So the negative sign is important. This term here is now little a to the 4th power. It's going to be big A to the 2nd power. What else? We have the velocity term, and now we have the resistance term. Now I'm in a position to substitute in all of the numbers. All right, so I get minus 0.2 to the 4th power. I get 100 to the 2nd power. The velocity was 3, and now the resistance of that loop was equal to 2. All right, you substitute in all the numbers, and hopefully I've done this correctly. I should get minus 24 newtons. Again, we know that the force here is in that negative x direction right here. So that there corresponds to choice A. Whew. All right, let's go to problem 3. Here's problem 3. We have a conducting bar of mass 0.3 kg slides with negligible friction along a pair of horizontal conducting tracks, separated by some distance d, which is 0.15 meters. The left side of the loop contains a resistor over here, which is 30 ohms, and there's a constant magnetic field pointing out of the page, which is 2 Tesla. First question says, what is the current through the resistor when the metallic bar is a distance of 0.225 meters from the edge sliding with a constant speed of 6 meters per second? All right, so how would you calculate the current? First of all, you need what is this induced EMF, and for that you can either look at the change in flux with respect to time, or we could just use the motional EMF equation. The motional EMF equation is B, what is the length of that rod, and multiplied by that velocity. But let's do the change in flux, and you'll see we're going to get this exact expression. So what do we have here? We have the rate of change of the flux. We have a B multiplied by the area of the loop. The area of the loop is the width, okay, it's W, multiplied by that distance d. Now, take out all the constants. So the magnetic field is uniform. The distance d, the length of that rod, is also uniform, so I remove those. And then I'm left with, how does the width of that loop change with respect to time? This is exactly what that velocity term is. Okay, so my induced EMF at the end is simply BdV. I'm looking for the current. So the current here is going to be the induced EMF divided by that value of the resistance. So we get BdV divided by that resistance. Just substitute in the numbers. Magnetic field is 2 Tesla. The distance d is 0.15 meters. The velocity we said was 6. And now my resistance is 30. Okay. Put in all the numbers into the calculator. I think you should get 0.06 amps. And that corresponds to choice A. All right, next problem says, what direction does the current flow when the bar is sliding to the right? Okay, when you're moving to the right, you have more flux that is going to be going through this loop right here. If there's more flux, it means, well, the loop wants to induce something that opposes that change in flux. So the B induced, for this case, if I wanted to oppose it, I want to generate an induced field that's opposite of that, okay? And the way that you get an induced magnetic field that is going to be into the page, for example, again, that's using the right-hand rule. You should have a current flowing in this direction here. That corresponds to the clockwise direction, up through the resistor. B is the correct answer for this one. All right, the resistor represents the filament in an incandescent bulb that requires 1.5 watts of power to light up. So this is what we want. We want our power to be 1.5 watts. What is the minimum speed at which the bar needs to slide in order to light the bulb? All right, so think about it. How do we get this amount of power dissipated? Well, our equation for power, remember from DC circuits, we had the resistance multiplied by the current squared. Okay, but the current depends on how fast you're moving, right? We saw that over here, right? This was our expression. So what we want to do now, we know our power is 1.5 watts. The resistance is 30 ohms. You can get to an expression here that is going to tell you what speed is required to have that amount of power. So right here, I'm going to substitute my expression for the current. This is BdV divided by the resistance. All right, once you square this term, and I have to isolate for what the speed is. So I'm going to be very, very careful here when I do this. So I'm going to get that the power, okay, I'm going to bring first, one of these resistance is going to cancel out. This is going to be resistance squared. Here I'm going to have a whole bunch of other squared terms. I have the B field that gets squared, and I have that distance that gets squared. Let me cancel out one of these resistance values. And don't forget at the end, I'm going to get V squared, so I need to take the square root of all of this. All right, so now we go ahead and we substitute 1.5 for here. I'm left with 30 ohms as my value of the resistance. The field is 2, that gets squared. And now we also have that distance is 0.15 meters, that also gets squared. All right, we put those numbers in the calculator, and I think you should get 22.4 meters per second. That's how fast you got to move in order to generate that much power, that much current that's required for the power to be 1.5 watts. E is the correct answer. All right, problem 4 says a copper wire with resistivity, given by this quantity, and a cross-sectional area, given by this number, is formed into a circular loop with a radius of 0.3 meters. The loop is rotating about the y-axis with a constant angular velocity omega in a uniform magnetic field pointing in the positive z direction coming out of the page. Okay, first thing they say is, what is the resistance of this loop? All right, the value of the resistance, if you're given the resistivity, it's given by that resistivity multiplied by the total length of this wire. In this case, the length is just the circumference of that wire, now divided by the cross-sectional area of that of the wire that we're using. And that's the value that we're given over here. So all we need to do here is just substitute in our numbers, 1.68 times 10 to the minus 8, multiplied by 2 pi, multiplied by 0.3. All of this is over 7.85 times 10 to the minus 5. Okay, you do all the algebra, you should get 4.03 times 10 to the minus 4 ohms. That means that A is the correct answer for this one. All right, at the instant shown in the loop, where that loop is in this XY plane, what we have here is the maximum amount of flux, right? They're asking you, what is the magnitude of the induced EMF? Well, the induced EMF, again, is given by, if I'm just worried about the magnitude of it, it's the rate of change of the flux with respect to time. But look at over here. If I was going to plot the flux with respect to time at that point, I probably have a maximum value right here, because the B field is, there's so many field lines going through that area of the loop. If I'm at a maximum B field with respect to time, it means, what is the slope over here? That the slope here is dB dt, and that there is 0. If this is 0, it means there is no change of flux with respect to time at that specific instant in time. So the induced EMF is 0, which means that, oh, that's it. That's all we need. It's 0. A is the correct answer for that one. All right, as the loop continues to rotate, the right side over here is coming out of the page, and the left side here is going into the page. Okay, what is the direction of the induced current? So let's think about what happens to the flux going through that loop when the right side comes out and the left side goes in. The flux gets reduced, right? The flux is reduced. So what would oppose that change in flux? The oppose of a reduction would be, well, let's induce a magnetic field that also points out of the page. What kind of current would produce that? If I have a current going in that counterclockwise direction, that would work. So that's choice A. All right, a second loop with twice the radius, so R2, little r2 is twice the radius of the first one, is created with the same type of copper wire, so the same resistivity and the same cross-sectional area. It's rotating with the same omega. Compare the current, the maximum current induced in that first loop to the second loop. All right, so if the radius is twice as big, it means that the resistance of that wire is also going to be twice as large. All right, so to compare the currents, I need to compare two things, right? The current for that second wire is going to be, well, what is the flux change? What is the induced EMF divided by that resistance R2? So let's go ahead now and look at how would you calculate this induced EMF if something is rotating like this. Again, I need to calculate what the change in flux is. Well, the flux for this loop, I would probably write it as this. The field is constant, okay? The area, I would just call it pi r squared. So, okay, that's the radius. I'm going to look at the flux for case 2. And what else? Now I need to figure out how to factor in this omega here. I would probably do something like this, cos of omega t. All right, so at time 0, I get that maximum flux. So what else do we have? Well, I'm interested now in how does the flux change with respect to time. I don't change any of these constant terms, so those could just remain the same. All right, what else? The omega will come outside. Again, I'm just worried about the magnitude, so let's not worry about any negative signs, but I should get, oops, let's put the omega, can't forget that. I get an omega that comes here, and then here I would have sine of omega t. All right, and I'm asking you for the maximum current, so we don't really have to worry about this term as well, because that's just the oscillation term. So I'll just forget about this right now if we're only worried about the maximum. So we need to put all these terms together. So let's go ahead now and calculate what this current is for the current I2. So here I would have the induced EMF, that's the field, multiplied by pi. Now, the radius is twice, right? So here we're going to get 2 times R1, and I square that, and the frequency is going to be the same for both cases. So now I divide that by R2, and R2 is twice what R1 is. Okay, so now we got to just take care of all of these other terms. Again, if the resistance is going to be 2 times, the radius is going to be 2 times. You see, you're going to get a factor of 4 that comes out here when I square this. Okay, so that it'll be a factor of 4, but the resistance was twice as big. And then here I'm left with all of the rest of the terms, omega and divided by R1. This term right here is nothing more than the maximum current in that original case. And the factor in the front, once you take this out, is going to be a factor of 2. So the correct answer for this, once you double that radius, sure, you've made the resistance bigger, but you've also made this induced EMF 4 times bigger, and you've increased the resistance only by a factor of 2. So your net maximum gain in current is going to be 2 times bigger than that previous case. All right, here's problem 5. A circular wire of radius and resistance R is placed within a time-dependent but uniform field at time t0 as seen in the figure below. All right, right here. Magnetic field is given by this expression. Notice that it has a time dependence. It's quadratic in time. It points out of the field. The radius is 5.5 centimeters. The resistance is 7 ohms. And that constant here that we need to calculate that magnetic field is 5 millitesla per second squared. Okay, so first thing they ask you, what is the magnetic flux through the wire at this specific time? So here we just apply our definition of the magnetic flux. Again, the field is uniform in space. Therefore, it's simply the magnetic field B and multiplied by the area of the loop. We don't have to worry about any angle here. So here I substitute the value, B0, T squared, and the area of the loop is pi R squared. Now we can go ahead and substitute in all our values. The magnetic flux, B0 now is 5, it's millitesla, so that's 10 to the minus 3. All right, to convert it to SI units, what else? The time now, we're looking specifically at this time point, 5.1 second. Have to square that value. And pi multiplied by the radius, 0.055 meters. All right, go ahead and substitute this. Okay, so what do we get? I think you should get something that is like 1.24 times 10 to the minus 3 Tesla meters squared. That there corresponds to choice A is the best choice for this. All right, next question says, what is the magnitude of this induced current at this specific time? Okay, so again, I have to think of Faraday's law, so I need to know what is the induced EMF and divided by that resistance of the loop. The resistance we're given is 7 ohms, so I'm now left to calculate what is the magnitude of this induced EMF. Again, I'm just worried about the magnitude, so for that I have to find what is the flux with respect to time, and then I have my 1 over the resistance term. Again, now the only thing changing here is this magnetic field. So the area doesn't change, so when you differentiate this, remember, I'm differentiating B times A and over 1 over R. I could take out the area from this derivative because that is a constant term, so I just write it as pi R squared. Let me bring the resistance term here to the front, and now I'm left with how does the field change with respect to time? Since this is just a simple polynomial, it's very easy to evaluate, right? The derivative of the field with respect to time is going to be that constant. And now I'm left with 2t. Okay, so this is really the key to this specific problem. And now you just substitute that for this expression right here. All right, so our last kind of algebraic formula down here is going to look like this. 2b0 and multiplied by t. And that is going to be the magnitude of that induced current. Now we can go ahead and substitute in all our values. We have pi 0.055 for the radius. I have that number 2. The B0 term for us was, again, this is 5 times 10 to the minus 3. And now I need the time. I'm looking at a different time than the previous problem. The time here is 3.7. Now I have to divide this entire thing by the radius of that loop, which is 7 ohms. All right, at the end, if you substitute in all the values, I think you should get like something like 5.02 times 10 to the minus 5. That there should be measured in amps because we've been working in SI units throughout the entire problem. So that looks like choice B is the best answer for that. All right, the next question says, as time increases, the heat dissipated in the loop. Okay, so for this one, I would think about heat dissipated in the loop as being the power, right? The more power there is dissipated through that resistor, the more heat will be generated. So think about the resistance is not changing. We're saying that this is basically a 7 ohm resistor. But what do you think is happening to the current? The current here depends on time. That means that the current here is increasing, which means that our power being dissipated through that resistor also increases. So for this one, C is the correct answer. Here's problem 6. We have a loop of wire with a radius of 0.25 meters and a resistivity 8 ohms per meter. Lies in the XY plane. The loop is fully contained in a spatially constant but time-varying magnetic field, and the graph is shown over here. Our first question is, what is the direction of this induced current at time equals to 8 seconds? So at time equals to 8 seconds is right here, but let's just look at what's going on here with that magnetic field. Right here, the field is getting smaller, right? And the field here is pointing out of the page. So it's going to mean that you're here in this region, you're going to get less flux going through that loop. We want to oppose that change in flux. So if there's less flux, it means that the B induced here has to be also out of the page to be opposite of that. I don't want there to be less flux, so I induce a magnetic field that is going out of the page. Use the right-hand rule, and you should determine that that current that produces this induced field coming out of the page needs to be in that counterclockwise direction. B is the correct answer. Next, they're asking you, what is the magnitude of that induced current at this time, at 1.5 seconds? So that looks like it appears right over here. So you're on this region where we're increasing the field as a function of time. So how would I calculate that? Well, the induced current is the induced EMF divided by the resistance of that loop. So let's think about the resistance here. Now, one thing that's a little bit different with this problem is they told you this. Now, resistivity, think about the units of here. This is 8 ohms per meter, okay? Usually, resistivity is given in units of ohm meters, okay? So we have to be a little bit careful with this one. So how would you get the total resistance if you're told that you have a resistivity, some kind of resistivity of 8 ohms per meter, is you need to take that resistivity and you need to multiply it by the total length of that wire. The total length of that wire is simply that circumference of the wire. So this is how you need to calculate the resistance here. Now for the induced EMF, well, that we're just going to use our change of flux with respect to time. Again, I'm only worried about the magnitude here. And now I can't forget about the resistance term. All right, so how do you calculate the change in flux? Well, it's always the same thing. In this case, the field is uniform, so it's simply B multiplied by the area of the loop and over the resistance. So the area is constant. That's not changing. You could take that outside. So we're left with pi r squared. And now this gets multiplied by the rate of change of the magnetic field with respect to time. All right, so what do we get? What is this value here in the bracket? This is really nothing more than the slope of the graph. So we go to the graph and look at the slope is uniform here in this first from 0 to 2 seconds. So my dB dt over there, very easy to calculate. Let me just do 4 divided by 2. 4 over 2 gives me 2 Tesla per second. All right, the field is increasing at 2 Tesla per second. All right, so we can now substitute in all our values. Okay, so what do we get? We get pi r squared here. We're going to get dB over dt. And the resistance here I just said was this resistivity multiplied by 2 pi r. Okay, so a lot of things could cancel out. The pi factors cancel out. One of these radii can cancel out. I'm left with this expression, and now I'm just going to substitute in my numbers. The radius was 0.25 meters. The slope of the graph we just calculated, that was 2. And now I'm left with this resistivity, which was 8 ohm meters. And there's still a factor of 2 here left over from that circumference. Those things cancel out. And at the end, I am left with my expression here, which is 0.0312 amps. All right, so the correct answer here corresponds to choice D. Next question says, compare the magnitude of the current at 4 seconds to 7 seconds. So let's see where 4 seconds is. 4 seconds is here. Wow, look what we have here. The slope over here is 0, which means that if I'm applying this equation, right, if there is no change of field with respect to time, it means the induced EMF is 0. So right away, you should be able to conclude that the current right here has to be 0. The current at 7 seconds is going to be down over here, but they're asking us just to compare the magnitudes. So we know that, oops, I said 7, but I wrote 4. Let's try that again. We know that this guy here is going to be some value. So it definitely is going to be bigger in magnitude than the current at 4 seconds. So that looks like it corresponds to choice B. All right, good problem. Let's go to the next one. Here's problem 7. We have a conducting bar of mass 0.7 kg was given an initial push and now slides with negligible friction along a pair of horizontal conducting tracks separated by a distance of 0.12 meters. The left side of the loop contains a resistor that has a resistance of 3 ohms, and there's a constant field of 1.4 Tesla directed into the page. The following questions pertain to the instant when the bar is at a distance d of 0.15 meters from the resistor, and the induced current here is observed to be 0.8 amps. All right, the first question is calculate the speed of the bar. All right, for these types of problems, we've done this quite a bit now. We know that the induced EMF, which you can calculate, again, just the magnitude of it is given by either the motional EMF equation, which is B times the length of that and multiplied by the speed. Okay, so that's pretty straightforward. Now, we're not told the induced EMF, but we are told the current, and we are told the value of the resistance. So at the end here, all we're solving for is what is that speed. So we have IR divided by the field multiplied by the length of that rod. Substitute in our values, we get 0.8. Resistance was 3. Field 1.4 Tesla. And the width of that bar was 0.12 meters. Go ahead and substitute in the values. We should get 14.3 meters per second. All right, and that there corresponds to choice B as being the correct answer. Next question says, what is the magnitude of the acceleration of the bar? Remember, it was just given some initial push. So what we have to do now is calculate the acceleration. Well, guess what? Newton's second law says if you look at all the forces acting on the bar, that must be equal to the mass times the acceleration. And in this case, the force is the magnetic force. So we have I multiplied by the length multiplied by the field. Again, my length here is nothing more than the width of that bar, W. All right, so we want to solve for acceleration. So this expression is going to be I, W multiplied by B, and divided by the mass. We know everything in this expression. 0.8. My width is 0.12. The magnetic field, again, 1.4 Tesla. And the mass of the bar is given here in the problem statement, 0.7 kg. Go ahead and substitute. You're going to get that the acceleration here for this problem should be 0.192 meters per second squared. That there corresponds to choice E. That's pretty straightforward calculation. All right, the next one says, in what direction does the current flow? So let's think about what is going on. Now keep in mind here the rod is moving this way. So there's going to be less flux going through that loop because the area is getting smaller. The direction of the induced field is such that it wants to oppose that. It doesn't want it to get smaller. So it would also create a B induced that would be going into the page. What kind of current would produce an induced magnetic field that goes into the page? You would need to have a current here that flows like this, and that corresponds to the clockwise direction. All right, here's problem 8. It says we have a long solenoid with conducting square loop in the center over here. The conducting wire with resistance 0.5 ohms is formed into a square, so that's inside over here. It has a side of 0.4 meters, is placed at the center of a long solenoid, which has a radius of 0.3 meters. The current through the solenoid is adjusted so that the magnetic field varies like this, and they're giving us the graph. All right, if the current through the solenoid at time t equals to 1 second is 3.77 amps, what is the number of turns per meter wrapping of the solenoid? All right, so for this one, we have to go look up what does the field produced by a solenoid look like? The magnetic field produced by a solenoid is given by this expression. It's mu0, little n multiplied by the current going through the turns. Now, little n is what we call the total number of turns divided by the total length, right? It's like the turn density. So turns per meter are the units here for this. So this is really what we're trying to solve for. What is little n? All right, so we have Bs divided by mu0 multiplied by the current. If I know all of those values, I can now solve. The magnetic field is given by this time dependence, but look at, we're really looking only at 1 second. So the field at 1 second is really 1.2 Tesla. So that's pretty easy. So here you just do 1.2. Mu0 is 4 pi times 10 to the minus 7. And now the current at that time is also provided to us. That is 3.77 amps. So we put our numbers in the calculator for this one, and you should get something like 2.53 times 10 to the 5. That's measured in turns per meter. Okay, so that there looks like it corresponds to choice A. Next question says, what is the magnitude of the current induced in the loop at this time? All right, so what we have to do now is, again, we're looking for the induced current. We're going to do the same approach we've been doing all along. It's the induced EMF, the magnitude of it, divided by the resistance of that loop. The resistance we know is 0.5 ohms. The induced EMF is always the same, right? It's how does the flux change with respect to time. Again, the area of the loop is not changing. It's the area of the square loop now. We got to be careful. We're looking at the square loop, and that's a square, so it's simply a squared. The only thing we're left with is what is this rate of change of the magnetic field? We know that B varies as 1.2 divided by t squared. Well, that means that dB over dt, again, just worrying about the magnitude of it, should be 2 multiplied by 1.2 and divided by t cubed. So we have to go ahead now and substitute this entire thing right into our expression right here. All right, so we get our last formula for induced current is A squared divided by that resistance. And now I'll just go ahead and substitute in all of these terms. I guess I could just substitute the numbers in right away. Save us a step. All right, so A squared would be 0.4 squared. The resistance we're given as 0.45. The rate of change now of that magnetic field was 2 multiplied by 1.2. And the time that we're looking at here is 1.3 seconds. And this is a weird one. I have to cube that term. All right, I think if you go ahead and you substitute in all our values into the calculator, you get something like 0.388 amps. All right, and that there looks like it corresponds to choice A. All right, the last question for this problem says, if the direction of the current in the solenoid is clockwise, so that is kind of shown up here. So that's the current in the solenoid viewed from the front. What is the direction of the current induced in the square loop? Okay, so let's think about what the field produced by this current in the solenoid is looking like. The field produced by the solenoid, I'll do it over here in blue, but that should be a field going into the page everywhere inside. All right, so what is the field doing? The field is doing this, right? So the field is getting smaller. Guess what? We want to induce a current that opposes the change in flux. If the field is getting smaller with respect to time, it means that the flux through the loop is also getting smaller. So we want to induce a magnetic field that is also into the page like this, that opposes the change in flux. So what type of current would produce an induced magnetic field that's into the page? That would be a current going like this in the clockwise direction. That is an application of Lenz's law right there. All right, that's it for this problem. Let's go to the last problem. All right, here's our last problem. We have a wire with a mass of 0.4 kg. The width of that wire is 1.5 meters and the height is 0.8. It's released from rest just above a region of uniform magnetic field of 2.5 Tesla directed into the page. There is no magnetic field outside of this region. The gravitational force causes the loop to fall, and its motion is constrained to the XY plane. All right, at the moment shown in the diagram, the loop is partially in the magnetic field and is observed to be moving at a speed of 1.2 meters per second. The magnitude of the current induced in that loop is 0.74 amps. Our first question is, what is the resistance of that loop? Again, if you think about my induced EMF, that would simply cause a current to go, and the relationship would look something like this. All right, resistance times the current. In this case now, I'm asked to solve for the resistance, so that's just the induced EMF in that loop divided by the magnitude of that current, which we know is 0.74 amps. So how would you calculate the induced EMF? You can use motional EMF for this problem or look at the change in flux again. It really doesn't matter. The change in flux, I would write as d phi dt. And here I'm left with 1 over the current. All right, so how would you calculate the change in flux? Again, it's the area that is changing, and it's really this height here that is the part that's here inside this field that's changing with respect to time. So the change in flux here, the field is constant. The width is constant. The only thing changing now is this height, and that the rate of change of that is nothing more than the speed of that loop. All right, and now I have to divide by the total current. All right, so this is similar to what we've done before. Now we go ahead and we substitute the numbers. You get 2.5 Tesla for here. The width is 1.5 meters. The speed is observed to be moving at 1.2 meters, and my current was 0.74. All right, we substitute the values in here, and we should get a resistance, which is 6.08 ohms. That there corresponds to choice E. All right, at the position shown in the figure, the induced current in the loop is counterclockwise or clockwise. Well, let's just see what is going on. As the loop is falling, guess what? There is more flux going through the loop, right? We want to generate a current that opposes that change in flux. So this is Lenz's law at work here. The induced magnetic field now should be coming out of the page. So that would be B induced, the direction of it. Now you use your right-hand rule. What kind of current would produce a magnetic field inside that loop that's coming out of the page? You would have to have a counterclockwise current. So A is the correct answer for this one. All right, last one says, at the moment shown in the figure and described in the text, what is the magnitude of the acceleration of that loop? Well, that smells a lot like Newton's second law to me. Here's my loop. I know that there is a weight acting down. And let's think about it now. If I have a current flowing like this, right, flowing to the right, that means there's going to be a magnetic force acting on it. The magnetic force acting on that loop now should be pointing up, is what you should find, FB. To find the acceleration, you should always think of Newton's second law. MA is equal to mg minus FB. Here I've taken down to be my positive direction in the direction of the acceleration. The magnetic force for this problem here is, well, that's easy. It's just I. What is the length here? IL cross B. The length is the width and multiplied by the field. To get the acceleration, you just divide through by the mass, and you're left with this, 9.8 minus IWB divided by the mass. Just substitute in the numbers. 9.8 for the acceleration due to gravity. The current is 0.74. The width, again, was 1.5 meters. It is placed in a field of 2.5 Tesla, and that gets divided by the mass, which in this case is 0.4. Go ahead and substitute that. You should get something like 2.86 meters per second squared. All right, and that corresponds to choice B. All right, folks, that completes the problem set on magnetic induction and Faraday's law. Hopefully you enjoyed it. We'll see you next time.